Okay, let's unpack this. Imagine a single, like a misconfigured wire taking down the entire banking system of a small country in just a matter of milliseconds. We usually think of the internet as this invincible, seamless cloud. But beneath that illusion of stability is well, it's a remarkably fragile set of architectural
Right.
rules.
And what's fascinating here is just how precise those rules have to be.
Yeah.
I mean, the cloud isn't magic.
Yeah.
It's a massive physical machine governed by unforgiving engineering protocols.
Yeah.
So if a service provider gets just one encapsulation header wrong
Hmm.
or, miscalculates the spanning tree transition, that seamless experience just violently unravels
Right.
and it brings enterprise networks to a complete standstill.
Which is exactly why we are diving so deeply into this hidden architecture today. We are taking a deliberate analytical journey through 10 specific practice questions for the 4A0-105 exam. And we are not rushing this. We are going to thoroughly unpack the underlying mechanics of virtual private local area network services, or VPLS, to understand how providers solve these catastrophic logistical problems at a microscopic scale.
I'm really looking forward to this because
Uh-huh.
these aren't just arbitrary trivia questions.
Right.
They are the fundamental blueprints of complex network architecture. By understanding these edge case scenarios, we can see exactly where the theoretical designs of networking collide with physical real-world constraints.
Yeah, let's get right into those physical constraints, starting with the data itself. So, question one. Large customer frames cross a virtual private local area network service successfully until traffic switches to a protected transport path. Smaller frames continue to work after the switch. What is the most likely cause? The correct answer is C.
Right, so the mechanism at play here is a maximum transmission unit, or MTU, mismatch.
Right.
The protected transport path simply has a smaller effective MTU than the primary path.
Mm.
Because when a provider sends a customer's data across a VPLS, they don't just send the raw Ethernet frame.
They have to wrap it in something.
Exactly. They have to encapsulate it with VPLS and MPLS headers to write it through the core network. And this adds physical size, like overhead, to the packet.
Ah, I see.
So when traffic moves to the backup path with the smaller MTU limit, those newly encapsulated large frames suddenly exceed the maximum allowable size. So the hardware simply drops them.
Wow.
The smaller frames, though, they have enough clearance to accommodate the extra headers, so they pass through unscathed.
Okay, so it's kind of like trying to fit a package into a mailbox.
Yeah, exactly.
It fits fine normally, but suddenly it gets wrapped in all these extra layers of thick bubble wrap for the encapsulation, and now the large packages just bounce back, but the small ones still fit fine.
That is a perfect analogy.
Yeah.
And to take that further, the most dangerous part of this MTU mismatch is that it often fails silently. It creates a network black hole. The routing protocols exchange small hello packets perfectly fine, so the network monitors report the backup link as healthy.
Right, because those are tiny.
Exactly.
Uh-huh.
But the moment a user tries to transfer a large database file, the data just vanishes into the ether.
So if simply wrapping the data in routing instructions causes sizing issues, how do providers keep millions of these packages from getting mixed up in the first place? Let's see how the exam tests this concept. Question 2. A provider carries services for several organizations over the same physical access port. Different organizations may use identical inner service tags, so the provider must also examine an outer service tag to distinguish them. Which attachment design meets this requirement? The correct answer is A.
Yeah, so this requires stacked VLAN tagging,
Okay.
which is universally known in the industry as KIN-Q. The provider inserts an outer tag, a service provider VLAN or SVLAN, while preserving the customer's original inner tag, the CVLAN.
Got it.
Because multiple enterprises are feeding into the same physical provider edge switch, there's a very high probability of overlapping VLAN IDs. Like, if customer X and customer Y both use VLAN 100 for their internal voice traffic.
Oh, that would be a mess.
Right. So the provider switch relies entirely on that outer SVLAN tag to keep those identical inner tags strictly isolated into the correct service access point.
But wait, why wouldn't the provider just force everyone to use different inner tags? Like, just mandate that customer X uses 100 and customer Y uses 200?
Well, because you cannot dictate internal architecture to an enterprise client.
Oh, true.
If you're onboarding a massive financial institution, they might have thousands of switches and legacy applications hard-coded to specific VLANs across dozens of data centers.
Yeah, that would be a nightmare to change.
It would require months of downtime and millions of dollars. The provider's job is to offer a transparent service, so the customer hands over their traffic and the provider wraps it in their own outer routing tag. keeping the customer's internal topology completely untouched.
Okay, so we've successfully isolated the traffic using KingQ, but what happens when an identity seems to be in two places at once? Question 3. The same customer hardware address repeatedly moves between two service attachments, and traffic to the device becomes intermittent. What is the most likely underlying problem? The correct answer is D.
So this is a textbook description of MA flapping.
MA flapping. Oh,
Yeah. In an Ethernet network, switches build a content addressable memory table, a CAM table, that maps a device's unique MAC address to a specific physical port.
right.
When a MAC address constantly moves between two different service access points, it almost always indicates a bridging loop on a customer's side or incorrectly active redundant path presenting the exact same source address at both attachments.
So it's like a panicked air traffic controller.
Yeah.
Exactly. Like it sees a plane approaching on runway A, writes it down, but a microsecond later, because of that loop, the exact same plane echoes back and appears to be approaching on runway B.
Yes. And the critical thing there is the physical hardware strain. Every single time that frame arrives on a different port, the switch has to flush the old entry from the CAM table and write a new one.
Oh, wow.
In a severe loop, this happens thousands of times a second.
Which completely explains the intermittent traffic. If I'm trying to send a file to that device, the provider switch is constantly fluctuating on where to send my data.
Right.
Half my packets go to the valid port and the other half gets sent down the looped path and just drop.
Exactly. The CPU utilization on the switch spikes to near 100% just trying to keep the CAM table updated, which degrades performance for every other customer sharing that hardware.
Yeah.
So fixing misdirected traffic is absolute priority one.
But what if we want to intentionally misdirect it? Or, selectively divert it for a specific operational purpose? Question 4. A provider must redirect selected customer traffic through an inspection service while allowing all other traffic to follow normal bridge forwarding. The selection must depend on traffic characteristics rather than the learned destination hardware address. Which mechanism should be used? The correct answer is B.
So the required mechanism here is policy-based forwarding, or PBF. As we just noted, normal bridge forwarding relies entirely on the destination MAC address to make routing decisions.
Right.
PBF overrides that default behavior. It intercepts the traffic on the data plane and evaluates it against configured criteria, like source IP, TCP port, or protocol type.
Okay.
If a packet matches the policy, it's forcefully redirected to a specific next hop, like a firewall or an intrusion prevention system, regardless of what its destination MAC address actually says.
Okay, so this isn't just a simple detour. It's more like a specialized logistics lane. Normal forwarding is like trucks reading highway signs and taking the most direct route. But policy-based forwarding is like the highway authority setting up a geofence that instantly diverts any truck carrying hazardous materials to a mandatory weigh station for inspection, while all the standard cargo trucks just keep moving at highway speeds.
That's precisely how it operates. It separates the control plane from the data plane logic.
Yeah.
You only want to subject highly specific, potentially vulnerable traffic to the latency of deep packet inspection.
Right, while leaving standard voice or video traffic on the fast, hardware-switched path.
Exactly.
So what does this all mean when these intentional paths fail? Like, how does the network recover without instantly causing those devastating ME flapping loops we talked about earlier? Question 5. A redundant path is blocked by rapid spanning tree. The current forwarding path then fails. What must happen before the blocked path begins forwarding customer traffic? The correct answer is A.
So when the primary forwarding path goes dark, the network has to activate the backup, which is governed by the Rapid Spanning Tree Protocol, or RSTP. But before that blocked port can actually start moving customer frames, the spanning tree must recalculate the topology and assign new port roles. The previously blocked port transitions through a highly controlled, specific sequence of states to ensure the network is loop-free before it opens the floodgates.
I have to admit, I've always found the naming here a little confusing. If it's the Rapid Spanning Tree Protocol, why is it waiting at all?
Right.
Why doesn't the switch just instantly flip the backup port to forwarding the millisecond the primary drops?
Because instant failover in layer 2 is incredibly dangerous.
Oh, really?
Yeah. If one switch flips its backup port to forwarding before the rest of the switches in the network have updated their topology maps, you create a momentary loop.
Ah.
And even a fraction of a second is enough to trigger a massive broadcast storm that multiplies exponentially and brings the entire network down. So RSTP is rapid compared to older legacy protocols, but it absolutely requires a methodical listening and learning phase to safely converge the network.
Got it. So it's taking a calculated pause to survey the battlefield before advancing.
Exactly.
That makes perfect sense. But that leads naturally to a massive scaling problem on the provider side. What happens when you have to manage those exact spanning tree calculations for dozens of different services sharing the same physical topology? Question 6. Many customer services share the same physical topology and must follow identical spanning tree decisions. The provider wants one topology change to produce consistent port states across all those services. Which design is most appropriate? The correct answer is C.
The appropriate design here is a management VPLS or MVPLS.
Okay.
If a provider has, say, 500 different customer VPLS instances running over the same physical links, running an independent spanning tree protocol for every single one of them would completely exhaust the router's control plane CPU.
That sounds heavy.
It is. So instead, they create one single management VPLS to carry the control information and handle the spanning tree calculations.
Right.
All the associated customer services are then tethered to it, simply inheriting the spanning tree decisions, ensuring consistency across the board.
So you basically abstract the complex math away from the individual data streams.
Yes.
If a physical link gets severed, the network processor doesn't have to calculate the failover state 500 separate times. It calculates it once in the MVPLS, and every associated customer service instantly syncs to the new safe path.
Exactly. It's a highly efficient use of control plane resources.
Yeah.
But, this raises an important question. What if we want to achieve redundancy without spanning tree artificially blocking our backup connections?
Because spanning tree forces you to leave expensive fiber optic links sitting completely dormant.
Yes, until a disaster happens.
Yeah.
And no enterprise wants to pay for a massive connection that spends 99% of its life turned off.
Right. Let's look at how providers engineer around that. Question 7. A customer switch connects to two different provider routers and treats both connections as one logical aggregated link. Traffic must continue through the remaining router if either provider router fails, without requiring spanning tree to block one connection. What behavior is required from the provider routers? The correct answer is B.
So this scenario describes multi-chassis link aggregation, or MC lag. To pull this off, the two physically distinct provider routers must constantly synchronize their operational and forwarding states across a dedicated inter-chassis link.
Okay.
They have to cooperate so intimately that they present a single, unified system ID to the customer switch.
Wow. So it's essentially a magic trick?
Kind of, yeah.
The customer switch thinks it's negotiating a standard link aggregation with one single router, completely unaware that it's actually balancing traffic across two entirely separate physical brains. It's like two horses pulling a carriage.
Ooh, I like that.
Yeah, they are synchronized so perfectly that the carriage driver interacts with them as a single engine.
That's a great way to put it. And the synchronization is the key to the illusion. By sharing state in real time, both links can be actively forwarding traffic simultaneously without spanning trees stepping in to block one.
So if one router fails, the other just takes over.
Instantly.
Yeah.
If router A loses power, router B is already fully aware of all the active sessions and takes the full traffic load. The customer switch just sees a reduction in total bandwidth, not a topology failure.
That is brilliant. But MCLAG isn't the only way to avoid using spanning trees, right? What about point-to-point connections? Question 8. A provider wants pseudowire redundancy without using spanning tree to select the transport path. The backup path must not create duplicate frames during normal operation. Which design satisfies these requirements? The correct answer is D.
So when dealing with pseudowires, providers use an active standby redundant model.
Okay, active standby.
Right. The primary pseudowire handles all the customer traffic under normal conditions to prevent loops. And the standby pseudowire is fully provisioned, but actively prevented from forwarding data. It only activates upon failure.
But why is the active standby model so critical here? With MCLAG, both paths were active. Why are duplicate frames such a catastrophic concern with pseudowires?
Because a pseudowire is essentially a blind tunnel ferrying raw layer 2 Ethernet frames. The provider network doesn't inspect the payload to manage sequence numbers like a layer 4 TCP connection would.
Okay.
So if you were to actively send the exact same frame down two parallel pseudowires to achieve redundancy, the receiving equipment on the customer side would process it twice.
Oh, man.
If that frame contains an instruction to execute a $1 million database transaction, processing it twice corrupts the data integrity of the enterprise.
That would be bad. So the active standby mechanism ensures absolute singularity of the data stream while still providing a rapid failover path. Well, here's where it gets really interesting. As networks grow massively, managing all these individual links becomes impossible. Question 9. A large service contains many access devices. Maintaining direct transport relationships between every pair of access devices creates excessive signaling and provisioning work. How does a hierarchical service design reduce this burden? The correct answer is A.
So this question explores hierarchical VPLS. A standard VPLS operates on a full mesh design, meaning every single provider edge router must have a direct, dedicated pseudowire to every other router in the service.
Right.
But from a mathematical perspective, the number of required connections grows exponentially as you add nodes. It simply doesn't scale.
Yeah.
A hierarchical design completely changes the topology. It connects access devices to central aggregation points using simpler connections. Those aggregation hubs then maintain the heavy full-mesh core transport relationships, which drastically reduces the signaling sessions.
Let's actually look at the math on a full mesh design because it is brutal.
It is.
The formula is n times n minus 1 divided by 2. So if an enterprise has 10 sites, the provider only needs to manage 45 pseudowires.
Right.
But if that enterprise expands to 100 sites, a full mesh requires nearly 5,000 individual manually provisioned connections. The signaling overhead alone would just crush the routers.
Exactly. Hierarchical VPLS converts an unmanageable spider web into an efficient system at the edges. By localizing the access connections, you drastically reduce the sheer number of signaling sessions the network has to continuously monitor.
But, scaling the connections is only half the battle. As these networks expand globally, scaling the actual memory of the hardware becomes the final challenge. Question 10. A provider connects many customer bridging sites, and core forwarding tables are becoming overloaded with customer hardware addresses. How does provider backbone bridging improve scalability? The correct answer is C.
This is where provider backbone bridging, or PBB, saves the core network. It works by encapsulating the customer's entire Ethernet frame with provider backbone MC addresses.
Okay, so it wraps it up again.
Exactly. Because the customer's original NK address is hidden inside the payload, the massive core transit routers only have to learn and maintain forwarding entries for the much smaller set of provider addresses.
So it's kind of like the postal service?
Oh, yeah.
The core sorting facility only routes by zip codes, the provider addresses, rather than keeping a database of every single citizen's individual name, the customer M addresses, in the entire country.
That is spot on. It isolates the complexity perfectly. The core network acts strictly as a high-speed transit backbone, totally unburdened by the millions of endpoint devices it's actually connecting.
Okay, well, to wrap up, the 4A0-105 exam material reveals the hidden architecture of the Internet. From the physical limitations of MTU overheads and QQ tagging, through managing traffic with policy-based routing and spanning trees, all the way to massive network scaling using hierarchical VPLS and backbone bridging.
It's an incredibly precise ecosystem. And as networks continue to exponentially grow, the reliance on these precise protocols for routing and encapsulating data becomes the absolute fragile lifeline of global communications.